Hey everyone, welcome to this. We're talking about assignment 28 today. That looks a little blurry. Oh, that's much better. Talking about assignment 28 today, we're continuing our conversation about integral as net change. So let's start with a little sort of warm-up thing. Okay, so here's a graph of velocity. Bump. That's 1. That's 2. That's 1. That's a big 1. 1, 2, 3, 4. Okay. And here, and here, and here. Okay. 1, 2, 3, 4. This is V measured in meters per second on this axis, and these are seconds over here. Okay, so this is a velocity function. So we know that x of 0 equals -3. So our particle's position at time equal to 0 is -3. All right, well, let's ask some questions about this. How about this? 1. Find x of 4. Okay, find x of 4. Come on, you've done enough of this. You can do this. Okay, so remember that x of 4 minus x of 0 equals the integral from 0 to 4 of v of t dt. Okay, so if I'm looking for x of 4, all I have to do is add x of 0 to both sides. And so now we have this. We're told that x of 0 is -3, but what about this integral? Well, this integral is this plus this. Okay, well, let's find that area. So this is 1 by 1, or 1. This is a trapezoid. Its height is 1. 1/2 height of 1, base 1 plus base 2. This is a triangle. 1/2 base of 1, height of 2. Plus, well, this does go to -2, by the way. 4 -2 is the word pair there. So we know that this is -2, and this is 1, so that 1/2, 1 times -2. Well, it turns out that this -1 and this +1 cancel each other out. 3 halves plus 1, 5 halves. 5 halves is 2.5 minus 3. So x of 4 is -1/2. Okay? Okay. So that was question 1. Find x of 4. How about the second question? Question 2. What's the displacement on the 4 seconds? Okay, give it a go. Okay, displacement. That's change in position. That's going to be x of 4 minus x of 0. Well, okay, we could also understand that as the integral from 0 to 4 of velocity. So what was that value again? Well, we know that's going to be 1 plus 3 halves plus 1 minus 1. And so I get 5 halves. And we've got meters here. position changed by 2.5 meters. And does that make sense in the context of the problem? Well, remember when we were looking just now for x of 4, and we knew that x of 0 was -3? Well, if I take -3 and I change that position by 2.5, when I get to x of 4, this particle has a position of -1/2. Okay. The last question I want to ask is, what's the total distance traveled? So, pause the video, give it a try. Okay, so did you say the total distance traveled would be 1 plus 3/2 plus 1 plus 1? In the last two problems, this has been counted as -1. But because we're looking for total distance traveled, yeah, that's an area, that's an area, that's an area, that's an area. So I've got 3, 4.5. Okay? Okay. Good. You need to be comfortable with that. We're going to practice a bunch of that. But I was thinking that maybe we needed some practice with things that aren't velocity, but are just rates of change. So, for example, I had a problem, and I can't find it now, that dealt with petite oops. So, here it is. Okay, we've got C of t as 2.2 plus 1.1 to the t. This is consumption of potatoes and millions of bushels per year. Where this is the number of years since 1990. Okay? Yeah. So the question is, I guess the question is, do you see that this function is a rate function? It's bushels per year, millions of bushels per year. This is not bushels. This is not just millions of bushels consumed. This is the rate at which potatoes are being consumed, yeah? Okay. So, I want to know how many bushels consumed from 1990 to 2010. Okay? So how am I supposed to think about this? What am I supposed to do here? Any thoughts about that? So, I integrate a rate. Here's my rate. See? This is rate. Change in this over change in this, that's a rate function. So I'm going to integrate from 0 to 20, 2.2 plus 1.1 raised to the t. Okay, well, I'll pop the calculator. And I'll say integrate, please. 2.2 plus 1.1 raised to the t. And I want to integrate with respect to x from 0 to 20. And I end up with 104.092, 093. And this is millions of bushels. All right, so 104 million bushels were consumed from 1990 to 2010 in this country. Cool. All right, how about this? How about How about this? What if I know that W prime is W prime of t is the rate of growth of a child in pounds per year? And so my question is this. What's that mean? I'm not asking you to find a value for it. I'm asking you, what does it represent? What does that represent? What does it mean to integrate that rate? Well, let's think about it. This is pounds per year times years. Oh, I'm getting a total number of pounds. So we know from our use of FTC that this integral could be equal to this. W prime is the rate of growth in pounds per year. Well, this is going to be the weight of the child. And this is going to be the weight of the child in pounds. So what we're finding here is the change in the weight in pounds of the child from age 5 to age 10. Okay? I don't need to compute it. I just need to understand the notation and understand what I'm looking at. So how about this one? The integral from 0 to 120 of r of t dt, and we know that r is the rate at which oil leaks from a tank in gallons per minute. Okay? So, what's this? What does that represent? That's right. If I integrate this rate, I'm going to have, right, because I'm doing gallons per minute, dt change in time, minutes, I'm getting gallons. So what I'm getting when I'm integrating here, when I'm integrating that rate, is how many gallons leaked from the tank in the first 120 minutes or 2 hours. Okay, good. Okay, so yeah, we need to understand this notation. We need to be comfortable with this notation. Don't worry, you'll be comfortable. We'll practice more. It'll be good. Okay, next. This problem. Can you see it? A car travels on a straight track, 0 to 60 seconds. The car's velocity measured in feet per second. See, velocity, feet per second. Acceleration, feet per second, continuous functions. That means continuous functions. Table above shows selected values. And using appropriate units, explain the meaning of the integral from 30 to 60 of v of t dt. Not v of t, absolute value of v of t dt. So what does that mean? What does that represent? What does it mean to look at the integral of v of t dt from a to b versus a to b absolute value of v of t dt? What's the difference between those two? Well, with this one, I'm getting s of b minus s of a. And that's a change in position from t equals a to t equals b. With this one, I mean, think about that first problem we did. Remember this one? And we said, okay, total distance traveled is this, plus this, plus this, minus this. In fact, I've said in another video that if we flipped that up and just found those areas, we would get total distance traveled. And what is the absolute value of velocity? This is a speed graph. And when we integrate a speed graph, we get total distance traveled. And that's fabulous and cool. But generally speaking, if I'm not with a calculator, I would much prefer to write this as a bunch of integrals, one for each of those regions. Like when we were looking here, integral from 0 to 3 of t dt minus the integral from 3 to 4 of u of t dt. Why minus? Because when I integrate here, I'm going to get a negative number. But I'm looking for total distance, so I need that negative number to actually be positive. So if I subtract that negative number, I get positive. Okay? Okay. We move on. Oh, and notice here, in addition to explaining what this means, by the way, this was from 2006 AP exam, they also then said, using a trapezoidal approximation with 3 subintervals determined by the table, we should approximate the value of that integral. Okay, so we're going from 30 to 60, and we're doing a bunch of trapezoids. So I'm going to say that the integral from 30 to 60 of absolute value of v dt is going to be 1/2 30 to 35, so 35 minus 30 times base 1 plus base 2. But look, it's absolute value, so this has to be 14 plus 10. There's our first trapezoid. Now our second trapezoid still has 1/2, but this time we're looking at 50 minus 35. And what can we say about heights? We can say heights are 10 plus 0. And finally our last one, 1/2, 60 minus 50 times 0 plus 10. Okay, there's our value, or our approximation. Yeah, I'm not going to go any further than this. I'm going to stop. The risk of me making a mistake, too great, so not worth the answer. But there's another question here. It says, using appropriate units, explain the meaning of the integral from 0 to 30 of a of t. 0 to 30 of a of t dt. What's that represent? Well, remember, acceleration is the derivative of velocity with respect to time, or v prime. Well, if I integrate v prime from 0 to 30, I know, according to the fundamental theorem of calculus, that that's going to be v of 30 minus v of 0. And what does that represent? Well, that represents the velocity at time equal to 0, and that represents the velocity at time equal to 30. And so what does this represent, or this, or this? Well, this is going to be a change in velocity. And here, by the way, we've got feet per second. We've got a change in velocity from 0 to 30 seconds. And that's what this integral represents. Can we calculate that integral? Sure, because look, it says here, find the exact value. Okay. Find the exact value. Interesting. Well, wait a second. wouldn't I just be doing some sort of an approximation? No, because I know that this integral is equal to this. Well, I know what v of 30 is, and I know what v of 0 is. So, I said in the last video, gosh, we're going to use this setup all the time. Guess what? Here it is again. Okay, so this is what they asked me to evaluate. I can't do it unless I'm using some sort of an approximation because there's no function to find the antiderivative of. However, because I know FTC2, I know I just need v of 30, which is negative 14, and I want to subtract v of 0, which is negative 20. And so I end up with minus 14 plus 20, or 6. And the units here are feet per second, because they're units of velocity. All right, and so what is it that represented? The change in velocity from 0 to 30. And positive 6 means my velocity increased by 6 feet per second from t equals 0 to t equals 30. Okay. We done that, we done that, we done that. I think I'd like to look at... No. That's one, I can't find it. I think that's it. Okay. There we go. Okay. So I thought it would be nice to dig into some more AP free response questions. This one is from 2018. It is with calculator. People enter a line for an escalator at a rate modeled by t equals 44 t over 100 to the third, 1 minus t over 300 to the seventh, and this is good from t equals 0 to 300. And then for t greater than 300, we're going to say 0. Nobody enters the line after 300. And these, by the way, are people per second. So these must be seconds. 300 seconds, that's 5 minutes. Okay. As people get on the escalator, they exit the line at a constant rate. Well, that's very interesting. So we've got this line of people, and some of them, they're all hopefully eventually going to go on this escalator and go up. And this is the rate at which people get in line. This is the rate at which this thing grows longer. Okay, this is our getting longer function. And we see that happens until time equals 300 seconds, after which the line doesn't grow any longer. But at the same time, they tell us they exit the line. Well, what does it mean to exit the line? It means it was finally their turn to go up the escalator. And we're going to say that they exit the line at a constant rate of 0.7 people per second. And at t equals 0, there are 20 people in line. Okay, so this is what we know. Okay, first question, how many people enter the line during the interval from 0 to 300? Well, this is the rate at which people enter the line, and I want to know the total number of people who enter the line. So what I'm looking for in part A is the integral from 0 to 300 of RT dt. I'm not worried about this part, just this part. Right? The first 5 minutes, how many people enter the line? It's a straight integral. College Board normally asks this kind of thing, and I think the hardest thing about this kind of problem is, can I type that function in properly? So 44 parentheses t divided by 100, close parentheses, raised to the third, times, parentheses 1 minus, t divided by 300, close parentheses, raised to the seventh, and there's our function. Okay, and this is what I want to integrate. So I'm going to go back here. I'm going to do math, integral, 1, comma x, comma 0, comma 300. And I get 270 people entered the line from 0 to 300 seconds. Okay, second question. During the time interval, there are always people in line for the escalator. How many people are in line at t equals 300? Well, wait a moment. So we've got two things going on here, remember. We've got people exiting the line, and we've got people entering the line. And what we're trying to figure out is how many people are in line at t equals 300. So, that's exciting. Okay, so this is going to be something very common for you. You're going to have a rate in minus a rate out. Yeah, rate in, rate out. And you could, of course, understand this as if I integrate rate in minus the integral of rate out. This is the total number of people who entered the line, and now we want to subtract the total number of people who left the line. Now, my experience is that while I can understand this problem that way, this is more often the way I see this. In fact, I wanted to find something called the number of people in line function. And that's going to be the integral of rate in minus rate out. So, if I want to know how many people are in line at t equals 300, I have to be a little careful because remember, when I integrate this, I'm getting the number of people, but what I'm really getting is 0 to 300. I'm really getting a of 300 minus a of 0. Because look, at time equal to 0, there are 20 people in line. So not only do I have to find this integral from 0 to 300 of rate in minus rate out, I got to add 20 to it because that was the original amount to get the ending amount at time equals 300. It is 300, right? Yes. Okay, good. So now I kind of also want to say this. We already calculated that part. So really all I need to do is integrate from 0 to 300 this rate out. Well, my rate out is a constant, 0.7 people per second. And when we integrate a constant, aren't we just taking b minus a times that constant? Okay, so 300 minus 0 times 0.7. And so I get 210. 210 people left the line, 270 people joined the line. So 270 minus 210 is 60, and don't forget to add that 20. Again, this is with calculator, so you could just do this integral on your calculator. Don't forget, though, it's this minus 0.7. Okay? So we're going to have 270 minus 210 plus 20 equals a of 300. And so 60 plus 20 is 80. There are 80 people in line at t equals 300 seconds. All right, what's next? For t greater than that, at what time are there no longer people in line for the escalator? Well, that's interesting. So this is my number of people in line function, right? or I guess I want to say, I want to change that a little bit. I'm going to say that the number of people in line, A of t minus A of 300 equals the integral from 300 to t. Now, remember, after 300, nobody is entering the line. So I just need to figure out that 0.7 dt. Okay? So, what do we want to know about this? We want the line to be equal to 0. So we want A of t to be equal to 0. All right, so that's going to be 0. This is the 80 we just found. And this is the number of people leaving, the rate at which they leave. So I've got negative 80 equals negative and 0.7 times t minus 300. Okay, doink, doink. Negative 80 equals negative 0.7 t plus 210. I'm going to subtract 210 from both sides. And I'm going to get negative 0.7 t equals negative 290. And if I divide both sides by 7/10 or multiply by 10 sevenths, boom, boom, negative times negative gives me positive. It looks like 2900 over 7. I wonder if I have a small mistake there. But that tells me when there would be no people in line. Okay? I mean, another way to think about this is, you know that at time equal to 300, there are these 80 people in line. And you know that you're having people get onto the escalator at 0.7 people per second. Well, how long is it going to take us to go through all 80 of those people? Well, let's think about it. 0.7 times t. I think I like that better, don't I? Because there's this many people we have to get through, and we're getting through them at a rate of 0.7. So if I divide both sides by 0.7, or 10 over 7, yeah, 800 over 7. That's a very different number. I like this number better. Yeah, I wish I could go back and look at that other one, but I just erased it all. Maybe you can, and let me know what I did wrong there. Put it in the comments down below. Okay, the last thing we have here, and no, don't worry about this on this next test. I mean, this is a lot of thinking to do. I just sort of want to start you getting ready for this, because these questions are really, really common on the AP exam. And remember how I had that A of t function, that amount function? That was equal to A of 0 plus the integral from 0 to t of rate in minus rate out dx. Okay, so that. Now, this amount function is really, really useful. We've used it already once, and really it's just FTC part 2. But now look here in part D. It says on 0 to 300, at what time is the number of people in line a minimum? Well, this is the number of people in line function. Rate in minus rate out plus how many ever you started with. This is my rate function for the number of people this is my number of people in line function. And I want to know when the number of people in line is a minimum, which means I need to find when a prime equals 0. So now I have to take the derivative of this. Okay. In order to find when a prime equals 0, I got to take the derivative of both sides. Now remember, a of 0 is a number, right? In this problem, there are 20 people in line. When I take the derivative of that number, I get 0. Now, what happens when I take the derivative with respect to time of this integral? Well, I end up with rate in minus rate out. Oh, well, that's interesting. And so really, since this is supposed to equal 0, I'm just looking for when does rate in equal rate out. Remember, this is with calculator. So I'm not expected to say, okay, 0.7, uh, where was it? There it is, 44 t over 100 cubed times 1 minus t over 300 to the 7th equals 0.7. No, I'm so not expected to do that algebraically. Really, this is the huge idea, that the amount function will have a minimum or maximum when a prime is equal to 0, and a prime equals 0 when these two rates equal each other. Now, when these rates equal each other, I don't necessarily know if I'm having a minimum or a maximum, but I can certainly build an a prime sign chart. Though first I think I need to find when this equals that. So I'm going to go back to my calculator, and I've got this rate in function already here. And now my rate out function. Now, what about a viewing window? Okay, because look, let's just take a look at Zoom Standard. What do you see? I know, utterly useless, isn't it? Right? So let's do some thinking about this. Our time is going from 0 to 300 seconds. And I'm going to go in chunks of 60 seconds. Now, our y values. Well, we just set this funky rate in function equal to 0.7. Well, I think all I need to do then is to set y minimum at 0 and y maximum at 1. And hit graph. So there's rate in, and I get these 2 points of intersection. Second, calculate, intercept. Okay. This number has to get closer to 0.7. There it is. 1, 2, 3. A prime values. 0, 33.013. Okay. And notice the graph is like this. Now it's going to be important in a moment. And then we have the second point of intersection, second calculate, intercept. And I'm just going to go forward until this y value gets closer and closer to 0.7. Almost there, so close. There it is. 1, 2, 3. And I get 166.575. And then we've got this other end over here at 300. Okay, now this is rate in. That's this curve. And this is rate out. Okay. Rate out is above rate in. That means the line is getting shorter. Rate in is above rate out, which means the line is getting longer. And from here, rate out is bigger than rate in, so the line is getting shorter. Now, what were we asked to find? To the nearest whole number, find the number of people in line. Oh, find the number of people at what time t is the line of number of people a minimum? Well, by looking at my amount prime function, I know that when a prime goes from positive to negative, this is when I have a maximum number of people in line. When a prime goes from negative to positive, though, I have a minimum. Watch out, though. We've got endpoints. Now, this endpoint, and then a prime is negative. I have a number, and then a decreases. That's a max. But this number over here, my a function is decreasing until I get to 300. This is a min. And they asked me to determine what the minimum number of people in line is. And I've got two minimums. And so really, what AP is looking for when they say find the number of people in line at this time and justify your answer, yeah, this is now a candidates test. And no, there's no candidates test on our next problem, but there is a candidates test going to be on the AP exam. So I want to know how many people are in line at 0. I want to know how many people are in line at 166.57575. Wish I hadn't erased that other number. I know it's 33 point something, but I don't remember what. 33 point, and I need a 300. One, two, three. And this is 33.013. Now, we know this number because they gave it to us in the stem of the problem, 20 people. But what about these others? Okay, well, I think we already figured this one out, 300. But here's what I'm really thinking about. I'm really thinking about this amount function. Amount of t minus amount of 0 equals the integral from 0 to t of rate in minus rate out dx. Okay? So I'm going to add that initial amount to these integrals. So this is going to be it's going to be 20 plus the integral from 0 to 33.013 rate in minus the rate out dt. Okay, so and here notice we have rate in, we have rate out. So I can think of this also as integrate. I'm integrating. Why is that here? Oh, grr. Why did I put that there? 44 t over 100 to the third. That's it. Okay. So back over here. Math, integrate. Okay, I want rate in minus rate out, comma, x, comma, 0, comma, 33.013. Okay. And so I get negative 16.196, and I think, well, that's wacky, except remember there were originally 20 people in line. So I'm going to add that 20, and I get 3.803, approximately 4 people in line at 33.013. And clearly this number is smaller than that number. We had our max, decreased until we got to 33.013 seconds. Now there are only 4 people in line. We expect this to be our maximum, so let's compute that. And we want y1 minus 0.7, comma x, comma 0, comma 166.575. And again, when I get this integral, 0 to 166.575 r minus 0.7 dt. When I get that integral value, 138.070, don't forget to add 20. And so we know that this value is 158.07. That's approximately 158 people. Definitely bigger than either of these two. But remember, at 300, we also have a minimum. So let's find out what that minimum value is. 0.7, comma, x, comma, 0, comma, 300, plus the 20 at the beginning, and that's the 80 that we found before. Yeah, this number is smaller than that number, but the absolute minimum occurs there. And so, guess what? This is my new optimization problem. I'm looking for a minimum. And the way AP wants us to find that minimum is kind of this really sucky thing called the candidates test. We tested all the critical numbers and the endpoints so that now we can say by the candidates test, the line has a minimum of 4 people, well, approximately 4 people at t equal 33.013 seconds. Okay? By the candidates test. Remember when I said explain? The candidates test is the explanation. We're testing all the critical values. Okay? So how did we do that again? Well, we said, hey, we want a prime equal to 0, and that meant that r in minus r out was equal to 0, or r out equals r in. Whenever these rates are equal to each other, I'm either going to have a minimum or a maximum. Okay, well, I guess that's not exactly true. And I think you see that in the homework problem with mice. Okay, well, so I wanted to give you a little preview about that. And we'll take a look at some more of these AP questions in our next video. All right, take care.